we need to introduce this expression or something more than that. Second, this correction from the gamma class actually doesn't depend on the topology, the submanifold that these D-branes and the wave-equal plane wrap on. It does depend only on the target space topology. And that strongly suggests that this correction from the gamma class actually has nothing to do with the physics of D-branes and the wave-equal plane. It has something to do with the target space property. Finally, when I look at this expression, two expressions, we can easily find additional term common in these two expressions, which is the e to the minus ij. The exponent is again purely imaginary. So based on these three observations, I strongly suggest that this correction from the gamma class has to be understood as a correction to this e to the minus ij. In other words, it has to be understood as alpha prime correction to the volume of the Calabi-Yau space rather than the shift of the Raman charge. There is other evidence which can support this claim, which is the two-sphere partition function. It's shown by these people that in the large volume limit, this two-sphere partition function can be written as the following form. Again, we can see this factor here. And here, it's very natural to identify this term as a correction to this volume of the Calabi-Yau, e to the minus ij, which will compute the volume of the Calabi-Yau space at the end. Furthermore, in the case of the Calabi-Yau 3 manifold, this two-sphere partition function, or e to the minus k is the exact Kähler potential of the Kähler modular space, it is known to be expanded in the following form. The first term is nothing but the classical volume of the Calabi-Yau manifold. And there is a second, it is already well known back in the 80s. And there is a second term which involves this Euler characteristic of the target space Calabi-Yau manifold, Calabi-Yau 3, and zeta of 3. These terms actually represent the Folder correction to the beta function in the nonlinear sigma model, whose target space is Calabi-Yau manifold. So it is already known as the paternity correction to the volume of the Calabi-Yau 3 manifold. One can show that this factor here, the range of the gamma class, actually reproduces this term. Exactly. So everything nicely fit into each other. Right? So in summary, we believe that this correction from the gamma class has to be understood as an alpha prime correction to the volume of the Calabi-Yau manifold rather than the shift of the Raman charge. So one-line method is forget the issue, just use the conventional form of the Raman charge of D-branes and vestibular coupling of D-brane without any further worries. So just forget the issue. So before I finish the talk, I know there is plenty of time left to me. Before I finish this talk, let me make one more comment. So this formula is actually valid in any dimensional Calabi-Yau space. So from these expressions, you can predict the paternity correction, alpha prime correction to the volume of the any dimensional Calabi-Yau space. And from that predictions, actually you can, you can predict the higher loop corrections beyond the full loop to the beta function of the nonlinear sigma model on higher dimensional Calabi-Yau manifold. I was told that there was some debate back in the 80s that whether or not there is a higher loop correction beyond the full loop. But I think these predictions strongly suggest that there must be some higher loop correction. So it would be very interesting to see or confirm this prediction by computing this paternity correction exactly, paternity correction in the nonlinear sigma model directly. Okay, let me summarize and give you some outlook. So today we computed this two-sphere partition function, hemisphere partition function, and real projective partition function and supersymmetric theory in 2 dimensions, especially gauge theories. And from this result, we can compute the exact metric on the Kähler moduli space of the Calabi-Yau manifold. In other words, we can compute the exact homological metric, including all kinds of Gaussian instant corrections. We can also compute the central charge of this D-branes in wave-equal plane, wrapping on some orthomorphic cycles in this Calabi-Yau manifold. And using this new exact result, we revisited the spherical familiar symmetries. We investigate this quantum phase of the gauge with a sigma model, we just found that there is a modification in the central charge formula in the large volume limit, which involves this gamma class. But we need to understand this correction as a alpha prime correction to volume of the Calabi-Yau space rather than the shift of the Raman charge. And this method provides a new and direct method to compute the stringent correction to the four-dimensional space in physics. So let me now move on to something which I didn't discuss today, but something very important to mention.
Sorry, can I still ask something about the previous lecture before this? So you say these higher order expanded gamma class only matters going above three-dimensional class.
Yeah.
Yeah.
Because it involves higher form.
Okay, but of course you can put type 2 string theory on top, maybe Calabi-Yau 5-fold. And can you use this to constrain 10-dimensional type 2 string effective action by derivative terms?
I think there's a relation to that too. Yeah. Higher order correction, the social verification, like that. I think this is usually very important in some cases. All right. So another important observable in the two-dimensional supersymmetric theory, especially two-dimensional conformal field theory, is this electric genus, which is defined by these expressions. That there is a trace of a Hilbert space in the Ramon sectors. We have -1 to the f, the usual stuff, and the chemical potential for left-moving U1 R charges and some other chemical potential for global symmetrical theory. Well, in the case of the compact conformal field theory, one can show that this elliptic genus counts some BPS state which are ground state in the right-moving sectors, but it could be arbitrary in the left-moving sectors. So it's something more than written index. And because of that, we can show that at least for this compact conformal field theory, this elliptic genus has to be holomorphic. Well, this elliptic genus formula for the Landau-Ginzburg theory has been very well known due to the work of the Witten, early 90s or late 80s, I'm not sure the year. But this elliptic genus formula for the supersymmetric gauge theory in 2 dimensions has been worked out very simply the last year by these two groups. And the formula is given by these expressions. W is the fiber of the gauge group. We have a Wonder determinant around the supersymmetric center point, which can be described as a flat connection of the two torus. But this Wonder correction contains lots of singularities. So to compute this elliptic genus, we need to do a certain residue operation on each of the singularities, which is called the Jeffrey-Cohen residue operations. Of course, today I won't discuss anything about this Jeffrey-Cohen residue. So one thing I want to emphasize here is that, of course, using this new exact result, we can reproduce the known result in the literature, something like elliptic genus of quintic field manifold or something like that. But we can also use this exact result to do something new. For instance, there is a paper by Gade and Guppo who used this exact result to understand whether a given supersymmetric QCD in preserving 0,2 supersymmetry have higher fixed point. We can also use this exact result to understand, how can I say this, to see there is some conjecture, I mean, I don't know how to say this one. So using this new exact result, we can also use this new exact result to find the existence of some quantum state which is not obvious and visible in the UV descriptions, but because of some other reason, the existence was conjectured. But using this new exact result, we can prove this existence too. But I found that it is also very useful to study the BPS spectrum of non-complex CFT as well. This is because there are some non-complex CFT, like a CIGA CFT or ALF CFTs, which allows this gauge in a sigma model descriptions. From there, we can compute the elliptic genus exactly for this non-complex CFT. Of course, in this case, because of this scattering state, we need to generalize this elliptic genus formula a little bit, and the elliptic genus turns out to be non-holomorphic, but still we have some exact result, and from that we can study this BPS spectrum with non-complex CFT in a systematic manner. And we can discover very interesting properties of this BPS spectrum, such as whole crossing and bulk modularity and so on and so forth. There's another thing which I didn't discuss much today, which is the Friedwitten anomalies. So as I said, when this D-brane is wrapping on some submanifold which is not spin but spin C manifold, there's some subtleties. This is basically because you cannot define a theory of fermions in this spin C manifold consistently. So because of that fluid Witten anomalies, Minasi and Moore found that there's additional factors in this D-brane charge which take into account this fluid Witten anomalies. So this one is the first chunk class of the normal bundles. And I was told that there was some debate, actually, whether or not this factor really exists in these D-brane charges. But I found that from this hemisphere partition function, this hemisphere partition function computation actually reproduces additional factors. So this is really there in these D-brane charges. But it also raised some other questions, something like, some using this TPOP anomaly inflow stuff, we can easily see that we need a similar term, even in the Ramon charge of the oriented plane. There are some paper by this Stella Fried Moore, which address these questions, but nothing is clear at the moment. So it would be very nice if this exact RP2 partition function says something about this sort of term in this oriented plane charges. And finally, let me discuss some open problem, small, tiny but cute problem. So we discussed about this regularization scheme dependence of this finite piece of this two-sphere partition function. Basically, we can ask the same question for this hemisphere partition function and the RP2 partition function. Of course, using this space-time picture, we already identified that this finite term of this hemisphere partition function and RP2 partition functions as a central charge or tension of this D-brane on orientable plane. But we didn't do any systematic analysis, something like this, something like what we discussed in the two-sphere partition function. So it would be very interesting. And if this finite term of this partition function is independent of this regularization scheme, then it would be a very interesting question what this quantity really means, or what is the physical meaning of this finite term of the hemisphere partition function and RP2 partition function without relying on the space-time physics, just within the context of the conformal field theory in two dimensions. I think I already discussed about this part. And finally, today I didn't discuss much about this another supersymmetric theory in the two-sphere, preserving SU2/1, where another SU2/1, where this U1 can be identified as axial U1R symmetries. In this case, this two-sphere partition function depends on the complex parameter of the superpotential rather than the twisted superpotential. So in other way, it computes some scalar potential on the complex structure moduli space of the Calabi-Yau manifold. This is a little trivial. This is a classical quantity, so maybe this is not that interest. But when you compute the hemisphere partition function of this supersymmetric theory, it will tell us about the A-brane wrapping on the middle-dimensional cycles in the Calabi-Yau manifold, which still remains fully understood relatively. So it would be very interesting to investigate this hemisphere partition function for these supersymmetric theories. And I'm sure that there are many other interesting problems related to that, but I leave that at your home. So thank you very much, and thank you.
Any question or comments?
Another question. So you mentioned the wall crossing homogeneous non-convex FTs. What do you mean by that?
Oh, so it's something new for this non-complex CFT. So when you compute the genus of this ALF space, like a town, you get some non-holomorphic answer. There is a way to separate this discrete spectrum and the continuous spectrum. And somehow this discrete spectrum depends on the parameters of the CFT.
The discrete spectrum, which parameter?
So here, the spectrum of this parameter is the size of this terminal circle.
Okay.
Yeah. So maybe we can discuss in private conversation. It's a little technical. So we can easily see. I mean, this DP state. Maybe I can discuss. Because I have a bunch of planes, right?
That's right.
So this is a kind of terminal space. We can think about the string winding the circles at infinities. But you know, this winding the string in the string prefers to staple with the tip of this this terminus geometry because of the tensions. But when you have momentum along the circles, right? There's an angular momentum barrier, so that there is a balance between these two potentials, which gives us some stable BPS configurations. But I mean, depending on this momentum charge, there is no stable point. Then it disappears. Yeah, this kind of marginal stability can be seen from this elliptic field.
You say in this case, so you would just come out a one-dimensional moduli space, and you say there's actually a jump in the special normalizable states at some values of the radius.
Yes. I think this is the first thing showing this non-complexity. Yeah.
I see. So, okay, for LED space, of course, that's the infinite radius.
Infinite radius, there's no such issue. Yeah.
There's also no such issue in the cigar set.
Cigar, I haven't thought about it yet, but I don't know. Yeah, we need to think about it. But maybe there is, because the geometry itself is very similar.
No, but in that case, in cigar set, you cannot just adjust that radius. It's fixed by the.
Oh yeah, it's a fixed. This radius is fixed. Yeah, discrete. Yeah.
Actually, I also have a question about this slide. So, so for example, the point about IR fixed point and Gauss-Gukov, right? So are they trying to just calculate some, say, given some UV Lagrangian and they work out the index?
Yes.
But what if there's no IR fixed point? So you are saying they are trying to see if they are.
That part is a little
Then why are you actually calculating?
Inconclusive. Yeah, inconclusive for that. I mean, there are some examples where elliptic units become zero. And of course, it doesn't guarantee that there is no such a CFT.
Yeah, because the
there might be some cancellation between the boson and fermion state.
Right.
But because this is something more than Witten index, it's very unlikely to expect this huge cancellation. But again, it's inconclusive.
I see. And also another question is, can you put 0,4 on S2?
Chiral supersymmetry cannot be put on 2. Yeah.
Okay.
As far as I understand, but maybe it's too quick answer.
No, this reminds me of another thing about the LD space. If you look at the free overflow, you have more UPS states that can be genus from the sector than the one at cigar point.
Yeah, you mentioned it.
Yeah. So now, is that captured by the maybe the ALF in the small radius limit or something, or it may be the.
Oh, I don't know.
Or
you mean the small radius limit, not the.
When you speak of the ALE genus, that includes all the twisted sector contributions.
Yes.
And then you say as you make the circle smaller, do you lose?
Smaller, yeah,
it
changes.
But how does it change? You lose.
Yeah.
Oh, interesting. And then in the limit, when you shrink to zero size, you lose everything except for the ground states. Is that correct? Because the ground state is only enclosed for multiplet that exists in the cigar CFT. That's in the normalizable sector.
Looks so, but
I don't know how to connect that to cigar though, because they all have in that sector. I mean that doesn't have much to do with cigar.
This ALS space with small circle or.
I mean the cigar doesn't have anything to do with the ALF string circle.
Yeah.
But
it's studio to LS fibrane stuff. So it's a little confusing.
That is true. So if you deform the LD space, starting from free overflow point by turning on the B field, you can go to a singular limit in the CFT and moduli space where it's supposed to have this cigar effective disruption down the throat. I mean, just throat was developed. And presumably, and in doing that, you lose these some of these states that can be repeated again somehow goes away. Do you know how this?
No, I don't know. Yeah. Yes.
This morning, your Lagrangian has one over L term.
Yes.
And I don't remember, does it break some symmetry or it does not break any symmetry?
It preserves supersymmetry,
So
but it breaks the conformal symmetry.
it breaks conversion.
Yeah. And it also it's an imaginary term. This 1 over L correction is 1 over L term is imaginary actually.
Other questions? If no, let's thank the speaker again.